Hey everybody. Today we're going to go through a little bit of a different day. Today I'm going to argue to you we're not going to do one calculation all day. What we're going to do is we're going to talk about quadrilaterals and triangles, and I want to specifically talk about the properties of them. Where we're going to go for the next few days is you're going to have to prove that certain shapes are what they are. So for instance, at some point I'm going to ask you to prove that something is a rectangle. So in order to do that, we're going to have to talk about what are the properties of a rectangle. And we're going to do that with both quadrilaterals and triangles. So you have a page that looks like this out in front of you. I have given you some quick little diagrams of each of those. What I want you to do is to just think about what the properties would be that would allow you to identify each one of those shapes. On the back of the page, what I'd like you to do is jot down what you think would be the required properties to prove that that quadrilateral is that shape. And then we'll kind of come together and we'll sum some stuff up. So when I ask you to try to come up with how to prove that something is a quadrilateral, what I want you to think of is if you did the properties that you come up with, then the only possible shape that you could draw would be the one that I was asking. Okay, I know it's a little bit of a different day today, so don't be alarmed if you have a lot of confusion or if there's a lot of hesitation. We're going to go through some stuff together, okay? I want you to pause the video, and when we come back, I'm going to give you all of the properties of these quadrilaterals, okay? Pause it now. Okay, we're back. So what you see on the screen right now is our whole completed page. You'll see some side length markings and some parallel side markings in red on each diagram and blue. And then what you'll see is the official name for each one of those shapes, and in orange, the required properties, okay? What I want to do is I want to break down each pair and just take our time talking about each individual pair so we can kind of come to an understanding of what's required to meet the minimum requirements for each shape. Okay, let's jump in on that top row, the trapezoid and the kite. Okay, we're zooming in on that top row. And so all I'm going to do is I'm just going to kind of take that page and take a look at the top two. So there's our trapezoid and our kite. Now, what am I talking about when I say name the minimum properties required to identify the shape? If you look in red on the trapezoid, and I want you to focus on the trapezoid, I've marked two things. You'll see that I've marked side lengths, so my top side is a different length than my bottom side because I put on those individual side length markers. But then you'll also note that I marked that top side and that bottom side as being parallel with those arrows. So if we take a peek at that then, what a trapezoid is, for me to build a trapezoid, if I create any four-sided enclosed shape, that's a quadrilateral, where I have one pair of opposite sides that are parallel, and those opposite sides are different lengths. If I meet those two criteria, one pair of opposite sides that are parallel, and the opposite sides are different lengths, then the only possible shape that I could draw would be a trapezoid. So off to the right, what I'm going to do is I'm going to start drawing some stuff on your screen so you can just see what I'm talking about when I say the minimum properties required for that shape. So off on the right, what I'm going to do is I'm going to draw a pair of parallel lines, okay? You can just see it off on the right. There is one set and another set. If those parallel lines are the same length, then I could start to enclose that shape as a four-sided shape, and I can start to get maybe a rectangle. Maybe, if they're far enough apart, it could be a square. I could end up creating different quadrilaterals. However, if I just delete those last two sides that I did to close in the shape, if I were to go through and I was to say, no, I'm going to create a set of parallel sides, but I'm going to make one of those sides longer than the other, then maybe I end up getting something that looks like that. Well, if I was to now enclose that shape, I can only create a trapezoid. So that blue figure that I just drew off on the right, that quadrilateral, is a trapezoid. Now, you might look at that and you might go, but wait a second, like that doesn't look like that one because like look over off on the right side, like that's not the same. And it's okay. What I just drew on the right side, that blue figure, maybe it has a right angle there. Like maybe that's a right angle. That would just end up being a right trapezoid, a trapezoid with a right angle in it. And that's okay. It's still a trapezoid. So notice that as soon as I have one pair of sides that are parallel, but different lengths, then the only shape I could create is a trapezoid. Okay, that's what I'm talking about when I say what are the minimum properties that create that shape. Okay, I'm just going to get rid of that trapezoid off on the right, and I think, and I'm hoping, we have a better idea of what I'm talking about. Okay, now I want to turn our focus to the top right shape, our kite. Okay, so to look at our kite, the way that we can only create a kite, look at the diagram and look at the side length markings, is if I have this side the same length as this side, and then this side the same length as this side. That would give me a kite. Now, how do we end up saying those sides, like those sides that compare? If you can look in the orange underneath, that's where the word adjacent comes in. So when we talk about adjacent, adjacent is another way of saying beside. Notice back in the trapezoid, we used the word opposite because they were on opposite sides of the shape. On the kite, if we have sides that are beside each other, that is sides that touch each other, then those are adjacent. So if I just go and get rid of that blue now, and I'm going to lose my side length markings, so I'm going to put those back on just to make sure that we're good. Then there is one length, a different length, a different length. Then those side length markings, if I construct a shape where two of the sides that touch are the same length and the other two sides that touch are a different length but the same, then the only possible shape I could construct was a kite. If you tried to do that off on the side, then the second, and I'm just going to scroll across for a second, the second I make one side the same length as the other side, if those are the same length, now I have to try to construct that and close in that shape. Well, if I close in that shape with another length and another length that are side by side, that are different but the same, then I must have drawn a kite. Okay, there we go. We got the top row. Okay, I'm going to slide that back onto our screen, and then what I want to do is I want to jump into the middle row. I'm going to argue to you this is where things can get a little more complex. Okay, we're in the middle part now. So I want you to take a look at detail of what it takes to draw a parallelogram. And then what you're going to start to notice is a rectangle starts to look an awful lot like a parallelogram. And then if you even get down to the bottom of the page, you'll start to notice that a rhombus and a square start to look a lot. Okay, this is where, and we'll talk about this a little later in detail, this is where we start to get into these one-way arguments. Not two-direction arguments, but one-direction argument. I want you to focus in on a parallelogram right now. And I want you to really focus in on the fact that you have the word or in between. What that or means is if I create a four-sided shape that satisfies the first criteria, opposite sides are parallel, then I've drawn a parallelogram. If I create a four-sided enclosed shape with the second criteria, and opposite sides are the same length, then I've created a parallelogram. Now, what some people are going to do is they're going to start to go, but wait a second, that would also be a rectangle. And I'm going to go, yes, it could be a rectangle, but it doesn't mean that it has to be. So this is where we get into a one-direction argument, and I want to talk to you with regards to a one-direction versus two-direction argument. So hang tight as we kind of walk through this. So off on the side, we're going to kind of have this discussion, and it's a pretty well-known argument or example of an argument that talks one direction versus two. In math, quite often, we have our equal sign. And so we get really used to the fact that your left side equals your right side. So whether you go in that direction or your right side equals your left side, go in that direction, it doesn't matter. Because both sides are equal, it doesn't matter which way you look at that argument. The left equals the right equals the left. However, what we're getting into here are one-direction arguments. And I want to give you an example because it's going to be one that I talk about in class quite a bit. If I was to say to you that all poodles are dogs, and let me just put that word all in front because that's key. All poodles are dogs. Okay, would you agree with that? And I hope you would say yes. And so you say, okay, that's a true statement. But if I was to flip that argument and say, well, then therefore all dogs are poodles, I hope you would sit there and say, wait a second, that's not right. And there's lots of examples of dogs that aren't poodles. Exactly. That what we have is a one-direction argument. I can go in the direction of all poodles are dogs, but I can't flip it now and say, well, then therefore all dogs are poodles. No. So it's a one-direction argument. Well, that's what we're getting into right now when we start to talk about parallelograms versus our last three shapes. If you take a look just at the parallelogram and rectangle, the minimum requirements are the red or the blue. So let's start off on the top with the blue. Look at your parallelogram. All opposite sides are parallel. So if I was to construct a four-sided shape, it's enclosed, and I draw my opposite sides being parallel, then I've created a parallelogram. Done. Well, now look to the right. We're going to look at the rectangle. My rectangle's blue properties also show that opposite sides are parallel. So if I make my opposite sides parallel, check. Rectangle. Not quite. Look at that word in between. And. My rectangle has one other property. I'm just going to go onto that rectangle and zoom in a little bit so we can see that blue angle marker in the corner. The extra property that my rectangle has is that my adjacent sides have to be perpendicular. That, of course, is just another way to say we need the 90-degree angle in the corner. That a rectangle has to have that 90-degree angle in the corner to make sure that it is a rectangle, not just a parallelogram. So, quite often, a parallelogram is referred to as like a tilted rectangle. It's like a rectangle that's being pushed to the side. It's leaning. So I want to take a peek then and make sure that we're good with the one direction argument. If you look at my check marks, when I build a parallelogram, I've made my opposite sides parallel. That does not satisfy a rectangle because I only have the one check mark on the top property. I don't have the 90-degree angle in there. So all parallelograms are not rectangles. However, take a look at the right now. If I satisfy both of those properties and I make a rectangle, then I've made my opposite sides parallel, and I've actually gone a little bit further and I've made my adjacent sides perpendicular. Then I satisfied my top property, opposite sides being parallel, which was the property that I needed to create a parallelogram. So therefore, all rectangles are parallelograms. Okay, I know it can be a little confusing, but this is our poodles and dogs, right? All poodles are dogs, but not all dogs are poodles. All rectangles are parallelograms, but not all parallelograms are rectangles. And you can see that with the listed properties. Okay, I don't want to go into the same level of detail, but if you want to take a quick peek at the red side length markings, you could see the same thing. I didn't write it over for the rectangle, and you'll talk a little bit about why I didn't bother, because it's actually an awful lot more work. But we could have done the same thing in red. If you create a four-sided shape where each pair of opposite sides are the same length, I create a parallelogram. That would satisfy a rectangle, but only if the adjacent sides are still perpendicular. You can see that on that bottom right corner of my rectangle. Okay, I'm hoping if we continue to work our way through this, we can maybe add some extra clarity. Okay, I want to jump down to the bottom row. Okay, on your bottom row now, and I'm just going to keep the parallelogram and rectangle in at the top, but I want our focus to be our rhombus and our square. Look at what it takes to create a rhombus. A rhombus requires all sides to be equal length. Okay, I'm hoping we can see it. All sides equal length. Okay, well, a lot of us would sit there and say, well, that's a square. But notice, a rhombus could be tipped to the side. It could be leaning. So all sides having an equal length only satisfies part of the definition of a square. Look at the and. You also have to have that 90-degree angle in there. There's our adjacent sides being perpendicular again. So we come to another poodles and dogs argument. All squares are rhombuses, but not all rhombuses are squares. They could be leaning. Okay, I am hoping that that is helping you to get some of this clarity about what it takes to create a shape. Okay, what I want to do now is I want to look at the whole page in its entirety. There we're back to the whole page, and yes, it's a little bit small, I get it, but I want us to kind of see where we're going with it. Notice your trapezoid and your kite, they're kind of the oddballs. They're the ones that are quite a bit different. You know, a pair of opposite sides, different lengths. None of those other shapes have that. A pair of adjacent sides with the same length. None of those other sides have that. Well, I guess a square and a rhombus do, but not the two pairs of adjacent sides. Now what I want to do is I want to focus in on, take a peek at your parallelogram. Because those last four shapes are all parallelograms. Yes, a rectangle is a parallelogram. We've already talked about that. But a rhombus is also a parallelogram. It just happens to be a special parallelogram. Because the only way I can enclose that with four equal sides is also to say opposite sides are parallel, and that's a parallelogram. It just happens to be a special one. A square is also a parallelogram because its opposite sides are parallel. It just goes further and has four equal sides and a right angle in there. So those bottom four are where we really get into the poodles and dogs argument. That's where we're going to spend a lot of our time this unit. Okay, there's our quadrilaterals. I know it can be a little bit confusing, and I'm not really asking you to memorize all this stuff so much. I think we're going to work with it so much that we're going to be able to reason it out. What I want to do now, I want to change gears. Let's start talking about some triangles. Now, okay, you'll see a similar sort of sheet on your page right now, but now it's talking about triangles. At the bottom of the page, you'll also notice that we've got this section down here where we're going to put in some definitions to some terms that you're going to need to know. Okay? What I want us to do, I want us to go through and do something very similar to what we did with quadrilaterals. I want you to name each one of those shapes and try to jot down what you think the properties of those shapes would be to construct or identify those shapes. Okay? Pause the video now, and when we come back, it'll all be completed. Okay, we're back. So you'll see that I put the names of all of those triangles in purple. And underneath it, in orange, there's our properties for our triangles. Down in the bottom, don't let that be your focus yet. We'll get into some of the definitions of those terms in the bottom. I want your focus to be on those shapes. So let's jump in detail on our four triangles. Okay. You should be able to see you've got your equilateral triangle, which we should all be good with, that all sides are equal length. Our isosceles, only two sides are equal length. That's very important. The word only two sides. Don't just say two sides, only two sides are equal length, two and only two. Scalene has no equal side lengths. And then you take a look in the bottom right, we have our right triangle, where two sides are perpendicular. There's our 90-degree angle again. I do want to add, I could extend this a little bit and say that we could have a right isosceles triangle and combine those two if I were to say that that side length equals that side length. Then that is absolutely possible. I could also say that we have a right scalene triangle if we happen to know, hey, that angle was 90. However, I hope that we're good, that you cannot have an equilateral right triangle, that we've got that property from our past that says, hey, if all sides are equal, then all angles are equal. Therefore, all of those angles are 60 degrees. I cannot then have a right equilateral. Okay, I'm going to get rid of that to make sure we're good. There's your four triangles. Those are going to be the triangles you are responsible. I guess 5 if you add in the right isosceles, right scalene. But those are the triangles that you're going to be responsible for working with. Okay, now what I want to do is I want to jump to the bottom of the page and give you a chance to get down some definitions. Okay, you are going to be responsible for proving that something is a median. You are going to be responsible for building the equation of a median. I am not going to ask you to define a median. So I want to make sure that you're good, that I am never going to ask you to write out what you see in red. What I want you to focus in on is knowing what that property is. So a median is a line that runs from one vertex of a triangle to the opposite midpoint. Okay, that's a median. Okay, let's take a look at an altitude. An altitude is a line from one vertex that is perpendicular to the opposite side. That's an altitude. Lastly, there's something called a right bisector, and that is a line that intersects a line segment at 90 degrees through the midpoint. It's kind of made up of a combination of those two. It intersects the line segment at 90 degrees. The 90 degrees is why it's called right. And then you also have the bisect part. Bisect is a way of saying cuts exactly into two equal parts. That would have to be going through the midpoint. So right bisector, 90-degree angle through the midpoint. Okay, what I want us to do is to turn over our page on the back, because what I want to do is I want to draw a triangle ABC, and then we're going to put on a median, an altitude, and the right bisector. And I think by us drawing them on, it's going to give us a better idea of what those properties mean. Okay, so I want you to turn over your page. We're about to draw a big triangle. Here we go. Okay, so on the back of your page, I want you to draw the triangle ABC that I've drawn. Now, I want to make sure that you don't think that I'm fudging this in any way and making something very specific. Except, I want to make sure that we don't go and draw something a certain way, because I don't think we're going to really get the idea of median or altitude or right bisector. So, on about half of your page, I want this to be half of your page, I want you to draw on the triangle that you see in triangle ABC. I want you to draw the side AB considerably steeper than the side BC. Don't make it look like it's an isosceles triangle, and do not make it look like it's an equilateral triangle. If you do, we're not going to see these details. Okay, so what I want to make sure you do, make it look scalene, and make sure that side AB is steeper than side BC. Okay, pause the video, take a moment to match that same triangle. Okay, we're back. So what I want to do is I want to go through and construct the three properties we just listed below. So let's start with the top one. I'll call that the red one to match my colors. I'm going to draw on the median from vertex A to side BC. So it says it's a line from one vertex to the other, or to the opposite midpoint. So if I'm going to draw the midpoint from A, then it passes through A. What I now need to do is draw that to the midpoint of the opposite side. So if that was the midpoint of the opposite side, let's call that point M. Then my median would be the line that runs from A to the midpoint of BC. And I could show that that was the midpoint by saying the length from B to M is the same as the length from M to C. What I just drew on, based on the labels on my diagram, AM is a median. There we go. Okay, I'm hoping that that clarifies a little bit the official definition of a median. Okay, let's do the same thing with our altitude. I'm going to match my color, so I'm going to draw it in purple. An altitude is defined as a line from one vertex that is perpendicular to the opposite side. So let's draw this altitude from B. So that means that I'm going to draw it from one vertex to the opposite side. But I don't know where I hit the opposite side. It's not about where I hit the opposite side, like a median is. It's about how I hit the opposite side. Because it's an altitude, I have to hit it at a right angle. So really quickly, if I went and did this, I hope we're good that that is not an altitude, because this angle down here is not 90 degrees. So if I get rid of what I just drew, and I make sure that when I drop down that line, that I'm going to hit that opposite side at a right angle. And maybe I just call that point, I don't know, point P. Then that purple line you see is an altitude. It's a line from one vertex to the opposite side, and you hit at a right angle. Okay, there we go, nice. I hope that on our diagram we can now tell the difference between a median and an altitude. Okay, last part, a right bisector. Well, let's draw the right bisector then from vertex C. A right bisector is a line that intersects a line segment at 90 degrees through a midpoint. So I may be trying to draw my right bisector from C, but then what I notice is if I have to go through the line segment AB at its midpoint, so that would be those two side lengths the same, but I also have to hit at a right angle, then what I might find is my right bisector of side AB doesn't even cross through C. Yeah. So what you might notice then is your right bisector is a little different than your other properties. And if you look back into the definitions for them, then you'll notice there's nowhere in there that says that it has to run from a vertex. So when we go through to construct our right bisector, it's about the side we're going to intersect, not about the vertex. Okay, just to make sure that we're all good, I'm going to just clean up that last endpoint pretty good. And let's call that, I don't know, Q, so that our names all sound very different. Okay, there are those three properties. Now, I want to deal with some stuff really, really quick, and I'm going to try to go as fast as I can go. So if I took those definitions, and I know I'm making them kind of small, but I just made a little extra room on the bottom. I just want you to notice that if we went through and we constructed a really, really crude equilateral triangle, then you're going to notice a bunch of things. If I went to try to draw the median from A to BC, then I have to hit the middle. There's my median. But the issue becomes, I would actually end up hitting that side length at a perpendicular angle as well, which then means that my median is the same as my altitude. If I then went through and said, wait, I'm going to try to build the right bisector, notice that becomes the right bisector. So in an equilateral triangle, all three of those properties are the same. That's why I wanted to make sure that when you drew your triangle, you didn't draw what looked like an equilateral triangle, I don't think we would have got the idea out of it. Look back now on the triangle ABC that I asked you to draw and look down at point P. It is very clear that point P is not at the midpoint of side AC. Okay, we want to make sure we have that visual. Okay, the last part, and it comes down to one of those properties in detail, and I want to focus in on my altitude. I'm going to just get rid of that equilateral triangle for a second, and I'm going to draw a different type of triangle. I'm going to call this point A, but what I'm going to do is I'm going to build an obtuse triangle. Okay, if I focus in on the altitude, and I now try to draw an altitude from B to side AC, just like we did before, well then I need to draw a line that goes through B and hits the opposite side at a right angle. And what you'll notice is, if I try to hit that opposite side, then there is no way that I am hitting anywhere near what a right angle would be. None of those purples are a right angle. Okay, let me just get rid of that. The only way that I can actually go from B and hit, anywhere near a right angle is to actually go outside the triangle. If I drop straight down and I extend side AC, then I actually hit at a right angle. That when we talk about an altitude, it's possible to have an altitude outside your triangle, right? That would be the sort of property where we would use the height of that to find the area of triangle ABC, for instance. Okay, I don't think we're going to be automatic with those three properties right now. I think we're going to get really comfortable with them when we start to use them. Okay, we'll get lots of practice with that. Okay, I just want to change gears a little bit and have a bit of an overview as we go. Okay, I want to just kind of talk a little bit about determining a figure. So this is going to be a situation where I am going to tell you or give you a problem that tells you, like, point A has the coordinates 3, 5, and point B has the coordinates -1, 6, and point C and blah, 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 blah. And I'm going to ask you, what shape is it? And you're going to have to work your way through and try to determine what shape it is with proof. So how do we go through determining that shape? This is the last little overview that I want to talk about. Okay, what you see on the screen right now is like a little bit of a decision-making tree. If we know it's a quadrilateral, and you can see me just circle that up at the top, then what I want you to consider is breaking some things down into 3 big categories. Remember, your trapezoid and your kite are kind of the weird ones, right? Your trapezoid has 1 pair of opposite sides, not 2. The opposite sides are different length. No other shapes have that. Your kite has 2 pairs of sides that are equal, but they're the adjacent sides, not opposite. Where things become a little more complex is when we break into parallelogram. To prove that something's a parallelogram, opposite sides are parallel or opposite sides are equal length. That satisfies a parallelogram, you're good. But within that, maybe we have some special shapes. Like maybe it's a rhombus. So yes, opposite sides are equal length, but what if they're all the same length? Or what about if opposite sides are the same length, but they're different lengths? What if I take angles? What if in your parallelogram, there's a right angle? Well, now it's a rectangle. Oh, but what if all the same side lengths or all the side lengths are the same and there's a right angle? Now it's a square. So we need to be able to work our way through using some of those properties. What information do we need to be able to do that? Well, notice we've talked about side lengths. So you're going to have to be able to come up with the side length of a bunch of your line segments. Notice in blue, we've talked about perpendicular, about right angles. That means we're going to need slope. So we're going to have certain properties that we're going to need to find using length of a line segment and slope. Okay, last one, just dealing with triangles. I wanted to talk about triangles in a bit of a different way because triangles are different than quadrilaterals. Really what your focus should be on when we start to work through triangles is trying to find the least amount. Like that's me kind of saying to you, do the least amount of work possible to be able to show that something's a shape. So if we're talking about like a triangle, well then we know it's got 3 sides. Well, what's the least amount of work that you need to do to show that it's a right triangle? And I hope that we would say all we need is 1 pair of sides to be perpendicular. That means calculate your slopes. As soon as you see slopes that give us perpendicular sides, then you've proven it's a right triangle. Well, what if it's a scalene triangle? Well, now we don't care about angles. We care about side lengths. So now we need to find the length of each side length and show that they're different. What if it's an equilateral? Well, now we're finding the length of all the sides to show that they're the same. What if it's an isosceles triangle? Well, now we're finding 2 lengths that are the same. What if it's a right isosceles? Well, now we need 2 sides the same length, and we need to find a slope to show the right angle. Okay, so we've got a bunch of stuff that we need to consider. If we need a little reminder about the fact that perpendicular lines have slopes that are negative reciprocals, that is really messy, then I think we should be okay. Okay, the rest of your time is going to be dealt with being given a problem and having to either go through and prove it's a shape or try to identify that shape. Lastly, those 3 properties, median, altitude, right bisector, maybe we're going to have to come up with the equations of those. Okay? I wouldn't spend a whole lot of time trying to memorize what we've talked about today. I've thrown a lot of information at you. But what we want to do is we want to spend our time doing practice problems where then we just get so comfortable working with it, we don't have to worry about memorizing anything. Okay? A little bit different because you don't have practice with this. What you want to do now is you want to jump into our next lesson, our next activity, to be able to work through some problems and see this stuff in action. Okay? Jump into that next video whenever you can. Thanks for working through today.